Okay, so for this video, I wanted to go from the finite state machine to a circuit. All right, and I quickly discovered, oh, there's actually an issue with the way I've handled the reset condition. I would like to do one's hot, but the problem is, how do I load that initial one? So normally that's not a big deal because we normally have an initial state that you think of, you power up, you assume you go to that initial state, and then you run from there. But in this particular case, it's a little more subtle than that because I'm actually trying to do things into a state that I called init. All right, so a common way of handling this type of problem is to use, instead of one's hot, I think I've mentioned this before, but use almost one's hot. Almost all one hot. So by that we mean that when we have an initial reset, we end up having all flip-flops cleared. So that's why it's almost one's hot, because the initial condition does not have a single flip-flop that's hot. They're all cleared to 0. So that would mean I would need to modify this finite state machine a little bit, and let's move the reset to a different state called Q0. All right. The advantage of that is that it gives me a state to clear to. So if I hit reset and I cleared all the flip-flops, I would be in Q0. This is assigned to all zeros. And from there, I could transition to the init state on the next clock cycle. Okay, so I needed to make that change so that I could implement these control signals in the init state. It's kind of a subtle thing, but I think that in general for these kind of problems, let's handle it that way. Let's say we have a reset that's completely clear, all the flip-flops are 0, and the very next state takes you to whatever your first state in the state machine diagram is. I'll talk about this more in class. Okay, so once I made that modification, then I'm going to do one's hot for the rest of the circuit. I don't have to worry about the initial condition, but I would need a flip-flop to represent Q init, and it would be assigned to a 1 when I'm in the init state. I need a flip-flop for Q for state P. I need a flip-flop for state D and a flip-flop for state I. To get to the circuit, I would need to control the D inputs for all these states. So now it's a little more clear what to do, because if I'm in state Q0, I will always go to init as the next state. Okay, so if I'm looking at the init D flip-flop, I look at all the arrows that come into init. The only thing that's there is Q0. So that takes care of my init condition. Okay, so a little subtlety, but it's not hard. All right, so the next thing I need to do is figure out the control equations for QP. All right, so remember, I'm not showing the loopbacks. So I need to figure out what are the loopbacks in state P. All right, so I can get to state P from QP. How? Well, I noticed that I'm leaving on car in, car out bar. I'm also leaving on car out, car in bar. So the only other two conditions that are left are car out bar, car in bar, ORed with car out. Can't get this over enough. ANDed with car in. So put that all in parentheses. So in other words, if I don't have either a car going in or a car going out, I loop back. If I have a car going out at the same time that I have a car going in, I loop back to P. Okay, so that takes care of the loop back condition on P. All right, how else can I get to state P? All right, and so you look at this. If I'm in state I always go back to P. If I'm in state D, I always go back to P. All right, so that takes care of the QP condition. All right, so the next thing I need to do is take care of Q. I said Q, I meant D. All right, so the D flip-flop for the P state. Okay, so I need to next determine the D flip-flop input for the I state. Okay, so for the I state, what are the arrows coming in? The only arrow is from QP, and it's on the logic condition, car out, ended with car in bar. Ended with QP. So if I'm in QP and I get this condition, I would go to state I. So there's the flip-flop control equation there. Okay, and lastly, I need the D input for the D state. All right, and I can get to the D state on car in ended with car out bar from QP. That's the only arrow. I didn't draw the arrow. That's the only arrow coming in to state D. All right, so those are the once hot equations. All right, so the next thing I need to do is specify all the output equations. Okay, so notice I'm trying to control the signals S1, S0, load S, and so forth. All right, so that's not too hard once I have things in a once hot. So for example, I look at load S. When is load S equal to a 1? Well, I'm noticing here load S is equal to a 1 in this state, the I state, and here, and in the init state. So everything but state P. All right, so the logic there would just be Q init, because there's a load state there, Q increment, QI, and QD. So there's the load state. Okay, so S1, I have S1 equal to 0, or maybe not even relevant. So the only time I have S1 where I need to set that equal to a 1 is in state I. All right, so if I'm looking at S1, that'd be QI. And finally S0, I look at S0, the only place that is equal to a 1 is in state D. Okay, so this would be QD. All right, so these are the flip-flop control equations and the outputs. All right, so here's the box around that. Flip-flop control. So this is a circuit. These are the more machine outputs. They only depend on the states. And so this is the full circuit to implement this finite state machine for the parking lot problem.